Hello, class. Welcome back. This is lecture 14. Today we are talking about power series solutions. So this is a thing from calculus probably a long time ago that you haven't seen, called the power series, and we're going to use them to solve some new types of differential equations. And I will try to remind you of the things you need to know once we get there. Okay, so now we move on to, so we're still going to be studying linear, and they're still going to be homogeneous differential equations to make things simpler, but we're going to now have variable coefficients instead of constant coefficients. So things like this is, I think, called like standard form or something. So what's gone on is that you've manipulated it so that there's no functions of x next to the y prime. But sometimes they can start off as, and you'll see it like this too. So they'll use a of x to say functions of x. So they'll say that there's functions of x next to y double prime too. And then what you can do is you can just divide to make them, to change it into the other form. And there are some things that happen when you do that. So you have to sort of worry about it. But we'll get there later. Okay. So the idea is that most of these do not have what I would call nice solutions. So that means it's much more technical that, but meaning you can't just say like y equals blah, 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 stuff with x very easily. Like with sines and cosines or powers of x or exponentials or all those nice functions you've learned about for a long time. You can't just stick a bunch of them in there and then say that's the solution. It just, there is no way to write the solution like that. Instead, we have to use a power series. So let me just remind you of the idea of power series from a long time ago. So in like calculus, you would create a power series for a function that you already knew. So something like, you must have seen this or done this, you would say sine of x equals, and then you did something called a Taylor series expansion, and you figured out that there's some way to write sine as an infinite sum of powers of x to the n times coefficients of some kind. And this means that you were doing that around the point x equals 0. And then you would determine these somehow. And then the idea was, what you're doing is you're saying that sine can be thought of as this infinite sum around the point 0. And if you just plot, if you graph finite sums, so you, instead of going to infinity, you go to like 7 and you plot like the first 7 of these as a polynomial on a graph, what you'll see is it sort of looks like sine around the point 0. And then if you plot more, if you go out to 8, it looks even more like sine, and just forever, as far out as you go, it looks better and better. And because the power series converges to sine, meaning it looks exactly like sine as you go to infinity, then you are able to write that they're equal. So that was the idea in calculus typically. But here, like I just said, we don't know that our solutions look like nice functions like sine and cosine. So now what we're going to do is we'll assume a power series solution exists, meaning that we're assuming that there's a solution. We'll call it y of x or f of x, whatever you want. And we'll assume that you can write it as a power series, meaning you can write it as an infinite sum of like an infinite polynomial where there's some coefficients on each power of x, and you can center that at a, and that's what this is saying. So a power series is an infinite series of this form. So I should say that this power series is centered at a because of this x minus a thing. And just to remind you how power series works, so I did it earlier, but again, this means like you plug in 0 for n, you add, and then you plug in 1 for n, you add, plug in 2 for n, and you go on forever, infinitely. But then you have to worry a little bit, because when you have infinite series, they don't have to add up to a finite number. So you would have seen examples of that a long time ago. And so we only want to define the function when the power series does add up to a finite number, aka converges. And that has to do with something called the radius of convergence. So the function is only defined for values of x for which the power series converges. So the idea is if you plug in like 20, it might be too far away. If you check like y of 20, and you put 20 in here, then you might end up with something that doesn't converge, doesn't add up to a finite number. So then your function doesn't make sense over there. It only makes sense when it adds up to a finite number. And that is what you do in calculus. You figure out when this happens. You figure out for which x's the power series converges, and that is called finding the radius of convergence. So some quick review. The idea being that if I plug in x equals a, then this just becomes 0. So I just get 0 plus 0 plus 0 plus 0 forever. So I just get 0. So the sum converges to 0. And if I go away from a, then I want to see if it still converges to something. And I want to see how far away I can go from a. And then the interval of convergence is you subtract the radius and you add the radius. And then the endpoints you have to deal with separately sometimes, but that's for that class. So then the idea is like, okay, if I stay within this interval, then my function makes sense. So what that means for us is that this solution will only make sense if I stay in that interval. So there's all these background things to worry about, but we're gonna try not to get bogged down by them too much. Okay, so then when a power series solves a differential equation, it will only do so in this interval where the power series actually makes sense. Okay. And then I'll just say that there are also restrictions on the actual differential equation that tell you like when you can or cannot do this technique, but we're going to sort of just skip over it and just do ones where it works. Just for lack of time. That's okay. You can read the book if you want to see all the very tough details. Okay. So let's just see an example to see how this whole thing works. And we will start off with an example that we already know how to solve so that we can see that our answer makes sense. So we're going to determine a power series solution about, so we got to pick a center point, a equals 0. In this case, we're pretty much always going to pick 0 to make our lives easy. For y double prime plus y equals 0. So you should be able to check very quickly that you can use the characteristic equation method and get the solution. But we're going to try out a new thing. Okay, so what the idea is that we want a solution of the form of a power series. So what we're going to do is we're just going to plug in the power series and determine the coefficients, what they need to be. That's the idea. Okay, so it's centered at 0, so you can simplify this immediately. So just x to the n, so we'll do that. And now we're going to plug this into the dE. So we need the derivatives. Now, how do I take a derivative of this thing? Well, each term is just a number, a constant times x to the n. So what's the derivative of that? I just bring down the power. And then I subtract the power. And that's it. But that means that the first term, the 0 term, is just 0 times. So when I plug in 0, I'm going to get 0 times this. So the 0th term is not even there anymore. You can rewrite it like this if you want. Okay. And what's the second derivative? Same idea. Now I bring down another power of the x. And now the first two terms are gone. So I really could write it as starting at this at n equals 2, because n equals 1 and n equals 0 will both produce zeros. So I could write it like this if I want. Okay, so I got my second derivative, I got my function. So now I can plug it in. So y double prime plus y, these are going to get very, very long, equals these two sums added together. And now we're going to have to remember how to deal with adding power series together. Oops, this one will start. This one is this one up here. So there's the first one we started with. That's that. So this needs to equal 0. And so we're determining the coefficients Cn to make this add up to 0. But first, what we need to do is we need to add these, we need to stick these together somehow. So you may or may not remember how to do that. What we're going to do is we're going to need x to the n. We need them to both start, or have, sorry, we need them to both have the same power of x to make that happen. So what we can do is we can re-index, is one way to say it. Re-index the first one. So the idea is for re-indexing, you may have done this a long time ago, but just to remind you, oops, is if I want this to just be n, what do I need to change my n's into? That's the idea. And it might help to just write out a couple terms. There's also a cn there. So if I plug in 2, I get 2 times 2 minus 1, c2, x to the 2 minus 2. If I plug in the next term, which is 3, I get 3 times 3 minus 1, c3, x to the 3 minus 2, and so on like that. So now what I could do is I can think of this as starting at 0, and then I'm just adding 2 to each thing. So the trick is if I want this to start at n, I got to add 2 to it. But that means that I need to now start my sum at 2 less than before. And then this will work. So this 2, how do I get that 2 to show up now? If I plug in 0 first, I need it to be n plus 2. And then this next n needs to be an n plus 2 minus 1. And then my x to the n becomes n plus 2 minus 2. So just some tricks from long ago. And now we can simplify a bit. N plus 2, n plus 1, x to the n. Now we can add these two power series together. So then we have, so now we're here, n equals 0 to infinity. We got this one. Same form as the other one. Whoops, I keep dropping the CNs. They're there the whole time. Oh gosh, I dropped them a couple times. This becomes CN plus 2. I'll just stick them on that side for now. There, because I've changed all the n's to n plus 2s. Okay. And now this one, I didn't have to do anything. It already has x to the n. But now the point is I can combine these into one big power series. The idea is that you're factoring out x to the n from each term that you plug in, and then you end up with the two terms added together, and then x to the n outside of all that. Okay, so the trick here is that this side is just a bunch of powers of x added together. Sorry, x to the power n. Why did I do a subscript there? This is just a bunch of powers of x added together. So if you imagine if I just had like ax plus bx squared plus cx cubed, plus, I don't know, e, okay, I forgot the first number, plus dx to the fourth, and so on like that, and I set it equals 0, what would that mean? Well, in order to add up to 0, I need all of these coefficients to add up to 0, because I need all the x's to go away. So I would need all of these to equal 0. And the same thing happens here. This tells me that in order for this to be 0, the coefficients have to be 0. So this is a bit like the method of undetermined coefficients. So now I know all of my coefficients have to obey some equations, just like in that technique. So now I know that n plus 2, n plus 1 times cn plus 2 plus cn needs to add up to 0. No matter what n is, every n I plug in, this needs to be true. So I also should write that for my n start at 0. So I need this to be true for every single n. So now the trick is that I'm trying, we've got to keep our goal in mind. Is to try to solve for this guy in general. So it would be really nice if I could just say, oh, C0, that just happens to be 5. And then I could plug that in here, and that would tell me C2, because then I could solve for C2 by plugging in 5 there and 0 for n. So that would be nice, but that's not what's happening. Instead, what's going to happen is there are going to be two coefficients that I cannot solve for, but all the other coefficients can be written in terms of them. And we'll see how that works by just plugging in these numbers. Okay. So let's plug in values of n and see if we can find a pattern. That's going to be the general idea for these. So the starting point is 0. So if I plug in 0, let's see where I can do this nicely. So if I plug in 0, what do I get? I get that 2 times 1 times C2 plus C0 equals 0. So this tells me that I will be able to write C2 in terms of C0 or vice versa. And I'm going to do C2 in terms of C0. So if I subtract the C0 over and divide by, I'm going to leave it as 2 times 1, just you'll see why later. Then what I've said is I know how to write C2 if I know how to write C0, but I don't know what C0 is, so can't do anything else. Okay, now I'll plug in 1. And the same equation gets me 3 times 2 times C3 plus C1 equals 0. Same game, I'm going to solve for C1 in terms, or sorry, C3 in terms of C1. So if I subtract the C1 over, divide by 3 times 2, then I solve for C3 in terms of C1. And we'll see the next guy. This is called a recurrence relation, this thing that we figured out here, because I'm figuring out future terms in terms of previous terms. So n equals 2, when I plug that in, I get 4 times 3. Keep the pattern the same, times C4 plus C2 equals 0. But the trick is I already know C2 in terms of C0. So I can solve for C4 the same way I did here. So I subtract C2, divide by 4 times 3. But then I can go a step further now, and I can use that I already know C2 in terms of C0. So if I plug that in there, the denominator is just going to go underneath. So I'm going to quickly write that 2 times 1 also on the bottom down here. And then it maybe looks a bit familiar, and the negatives cancel. So there's a bunch of work to be shown here to establish the pattern. All right, so now let's do 3, just to do one more. So if I plug in 3 here, I get 5 times 4 times C5 plus C3 equals 0. And same idea, if I solve for the future one in terms of the previous one, so I solve for C5 by subtracting C3 and then dividing by 5 times 4, I can do a step further and realize I already figured out C3 in terms of C1 and plug that in too. And I get C1 over 5 times 4 times 3 times 2. Okay, so this is enough to establish the pattern of the coefficients. And that's our goal here. So one trick that we could have done earlier is you can write Cn plus 2 as negative Cn over n plus 2, n plus 1, so you don't have to keep dividing. So in the future, you should probably do something like that. Okay. But in any case, so what now? So now what this is saying is that any Cn in the future can be written in terms of either C0 or C1. So what do I mean? So pick any your favorite number. So if I pick C20, then I could write that in terms of C18 divided by some stuff. But then that C18 I could write in terms of C16 divided by more stuff from the previous terms until it goes all the way down until C0 times a bunch of stuff underneath. And we can see that that's the pattern being established here. So the next guy would be C6 would be written in terms of C4. And then I would be able to replace C4 with all of this stuff. So it takes me all the way back to C0. So what's happening is it depends on if the n is even or odd. So that's what we're going to break the cases into. So the pattern is C, if it's an even number, you can write it as 2 times k. That's the trick. So even numbers look like 2 times something. If it's even, what's going on? Well, let's see if we could figure out the pattern. 4, and what's this on the bottom here? 4 factorial. You may have recognized that before. So when I plug in an even number, this pattern will continue. So I'll get that exact number factorial on the bottom times C0. That's what happened here. But one extra thing is that this guy was positive for C4, but it was negative for C2. So we're going to have this flipping back and forth. So that's because I have to keep subtracting over here. So when is it positive? When is it negative? So it's positive at 2, but then it's negative at 4. Oh, sorry, it's negative at 2, positive at 4, then it'll be negative at 6. So I have to have some sort of -1 here, flipping back and forth. So if I plug in 0, or let's plug in 2 actually to check. So if I plug in 2, it's -1 squared is positive, and that corresponds to C4. So let's just see that I get the same thing. As I predicted up above, and I do, because it becomes positive. So I get that. Okay, so then for odds, very similar idea. So if I think about what I got for C3, I can establish, or C5, I can establish the pattern. So C5 looks like C1 over 5 factorial. So if I have an odd number, I'm going to divide by that odd number factorialed. And it's going to be in terms of C1. And then I'm also going to have this negative flipping back and forth. So C3 was negative C1, but C5 was positive C1. So I need a negative here. What power should I use? I'll use K and just check it, make sure that works. If I plug in K equals 2, I get C sub 5. And so the negatives cancel, which is good. And I get what I got earlier. Okay, so then the key is this. These are my formulas that tell me all the coefficients. So now I'm going to plug these back in. So a very long solution. The point was I started with not knowing anything about my CNs, my coefficients. But now what I know is if I write them out, oops, so let me just write out a bunch right here. So C0, x to the 0, plus C1, x to the 1, plus squared, plus C3, x cubed, plus C4. Let me write one more. Let's go out to 5. If I do that, and then I group up the evens, then I can write those ones all in terms of C0. So this is all just going to be all of these terms are being put together in this series. Oops, x to the n. So what I'm saying is I've figured out all of these C's, and they're just these things. These are all the C's. They're all in terms of the first C0. And then if I group the odd ones together, I can write those all as another infinite series. Where the coefficients are in terms of C1, the first C. Oops, so this should be x to the k, because now I've switched to k's. You could switch everything back to n's if you like. The index, the name of the index does not matter. Still picks out the same thing. So this is this power series solution. And note that it's a 2-parameter family, which is great. That's what we want. What are the 2 parameters? C0 and C1. Now, normally you might have called them C1 and C2 a long time ago when we solved it the other way. But they're just names of the coefficients, so it's okay either way. So that's that. That's the solution. But I said at the beginning, we did this one specifically so we could check our old solution. So if we solve y double prime plus y equals 0 using the characteristic equation, here's what you'll get. You'll get y equals, so I would have called it C1 cosine x plus C2 sine of x. So you do the characteristic equation, and we always called it C1 and C2, and this is what we would have got. Well, this is the same solution actually, which is good. You may not see why, but let me show you. It's because a long time ago in calculus, you learned how to write functions, nice functions, in terms of power series by using something called the Taylor series expansion. And it just so happens to turn out that if you write the series expansion of cosine, it's exactly the same as this stuff. So I just changed the letters, but it's the same. So this thing, if I take out the C0, this is just cosine of x. And guess what? This other series is secretly sine, which you may have also learned a long time ago. This is the series representation of sine. So if I just take out the C1, the rest of it is sine of x. So it is the same solution. One's in terms of power series and the other's not. So what's often the case is you don't know that this thing is already something else, and so you just leave it and that's your answer. But if you happen to know that it's the power series of some other easier function, then of course you could replace it. But most of the time it just looks like this giant thing after all is said and done. And what can you do with it? Well, you can like go on Desmos and graph out a few terms, like up to like 5 terms or something, because you can't graph infinitely many, and sort of see the solution taking shape. Okay, so let's do an example that we can't already do next. Lots of different things could happen. So let's solve with the power series solution about we'll just do 0 again. So here's a totally different one. X squared plus 1, y double prime, minus 4x y prime, plus 6y equals 0. So this one is not in the standard form, and there are some issues, but we're going to skip over all the issues and we're just going to do the steps. So you can divide by x squared plus 1 and write it the other way, but it's easier to work with if we don't. So we're going to leave it like this and just do the same process for some practice. So we're going to assume that there's a power series solution. And then determine the coefficients. So this all works the same. Take the derivatives. That you need. And plug them in. But now it looks a bit more complicated than the previous one, but actually it's going to turn out to be much easier, interestingly. So lots of things can happen. So I'm going to plug these in. It takes lots and lots of writing. So that y double prime goes there. Okay, minus 4x, y prime goes here. And then plus 6 of the original, just y. Now the key is to keep remembering, I'm trying to figure out a way to write Cn in general. And it could be that it breaks up into even and odd cases or something like that. Or we'll see in this case, it just all simplifies very nicely instead. Okay, so how do we start simplifying this thing? We want to try to get all this as one big series. That's the next step. And to do that here, let's focus on one at a time. So this is just multiplication. So I can distribute this guy in, and I can just multiply this 4x in, and I can multiply this 6 in. That's what we're going to do next. Okay, so where does that leave us? So now I have n times n minus 1 times Cn, and I've distributed it to the x squared. So I have x to the n minus 2 times x squared plus, and then I distribute it to the 1 1 times this power series is just the same power series. And then this 4x I'm bringing in, multiplying it in. I'll just write it in this order. And then this 6 I'm bringing in. Okay, now some nice stuff happens. What's x squared times x to the n minus 2? Well, you just add the powers and the 2's cancel, you get x to the n. What's x times x to the n minus 1? Also x to the n. And so what's nice is these already have x to the n's on 3 of them. It's just that this one doesn't. So let's change that to x to the n as well. That's the next step. Let me just check my notes because it's a lot of work, so I don't want to mess up an accident. I want to think about the easiest way. Yeah, let's do that. Okay, so how can I re-index this one? So if I just change, oh wait, that's a 2 there. Huh, almost screwed up. Good thing I checked. So I distributed this into that 1. So it's 1 times that, so it doesn't change at all. So that should still be a 2 there. That would have screwed up everything. Okay, so now I'm going to re-index by adding 2 to all the n's and subtracting 2 on the index. And now they're all x to the n's. Okay, so now the next issue is that they don't all start at 0. So this one starts at 0. This one starts at 0. That's good. These two don't. But this one, what happens if I plug in n equals 0 and n equals 1? I just get 0. So one way to change a power series to write out the first 2 terms, or first however many terms you need. So this power series is really 0 plus 0 plus, and then I start at the, and then I have the rest of the terms. But sorry. Yeah. So this 0 term I can think of as the n equals 1, and this is the n equals 0 case. So then I can just combine these into starting at 0. It doesn't change the power series. This one I already fixed. Okay, so that's just because if I add in the 0 in the first term, those are just giving you 0 anyway, so I can just add them in with no problem. Same thing happens here. If I just add in the 0th term, plugging in 0 gets you 0 there. So I can just start this one at 0. No issues. Let me put the 4 here next to the n. And this one already started at 0, so we're good there. Okay, so now they all look the same. Now we can combine them into one big old group. So let's do that. N times n minus 1 times Cn plus n plus 2 times n plus 1 Cn minus 4n Cn. Oh, wait. One of these should be a plus 2. Aha, very tricky. So when I re-indexed here, I added 2 to all the n's, so I could do that, but I forgot to add the 2 to this Cn. So that is still there. Almost got me. Okay, very easy to make mistakes here. Okay, so all of that times, now, so I've taken out my x to the n. And then the idea is the same. This all needs to be 0. You need all the coefficients to be 0. And what I'm going to do is I am going to multiply some stuff out and keep the CNs together. So this is going to be n squared minus n minus 4n plus 6. So I've combined the CN terms plus n plus 2, n plus 1, cn plus 2 equals 0. This guy this becomes minus 5n, and then it factors into n minus 3 and minus 2. And now we get this. Okay, so now I'm going to write the next term in terms of the previous one. So I'm going to solve for cn plus 2. So I subtract this guy over. And then I divide by the n plus 2, n plus 1. And this is what I need to happen for n equals 0, 1, 2, and so on. So again, we're going to plug in these values of n in order to establish a pattern, but we'll see the pattern is much easier to deal with than last time because a bunch of stuff goes away. So if I plug in 0, I get that C2 equals -3, -2 over 2 times 1 C0. So that becomes -3 C0. I plug in 1. Again, I'm going to get the third term in terms of the C1 now. So if I plug in 1, I get -2, -1 over 3 times 2, which is negatives cancel, I guess. Wait, what happened here? I think my work is slightly off. Okay, so the negatives should have canceled here. This should be a +3, and then this should be a 1/3 C1. Might be off by a negative for some reason. Okay. All right, let's plug in 2 here. And then we'll see the magic beginning. So if I plug in 2, I get -1 times 0. I don't care what the bottom is now because it's 0. 0 times C2, which is just 0. But then this tells us C6 is going to be something times C4, but C4 is 0, so C6 is going to be 0. Similarly, C8 will be 0. All the rest of the even ones will be 0. Same thing will happen with the odd ones. C5 is equal to plugging in 3, 0 times 3 minus 2 is 1. It doesn't matter what the bottom is now because the top is already 0. So 0 times C3 is 0. But then C5 tells you C7. So C7 is 0 times something, which is a 0. And so the rest of the odd ones will be 0 too. So now we don't have an infinite series anymore because the rest of them just become 0. So what do we have left? So now we go back to what we started with and we plug in what we know. So C0 x to the 0 plus C1 x to the 1 plus C2 x to the 2 plus C3 x to the 3. But then after that, it's going to be 0, C4 x to the 4, C5 x to the 5, and so on. These guys are all just 0. So our answer is just this. but we're going to rewrite the ones we know in terms of the previous ones. So we get C0 plus C1x plus C2. We can write in terms of C0. So this is 3C0 x squared now. And then C3 is 1/3 C1 x cubed. And then we're going to group the C0s together. So I get 1 plus 3x squared C0 plus the C1s together, x plus 1/3 x cubed C1. So this time my power series solution reduces down to just finite polynomials. And here's my 2-parameter family. So that can happen too, interestingly. All right. So just one last thing to remind you of, and there's lots more problems to do, but we'll do it next time. So again, one more thing. We are ignoring which values of x is this solution valid for. These are technical details that we are skipping. But I will give you the theorem, and I'll call it a fact about what's going on. So if the point that you're using, A, that you're centering around, is something called an ordinary point. So you can go look that up if you like. It's just an ordinary point. Just a point where basically you don't divide by 0. It's the idea of a differential equation of the form that we're dealing with. Then you can always find 2 linearly independent solutions in the form of power series. And that's what we did in these 2 examples, centered about A, which converges on some radius, some interval. And that's what we did today. We found 2 linearly independent solutions using this power series method both times. These are the 2 linearly independent solutions here. For this one, they are power series that just end very quickly. And then earlier we found sine and cosine as our 2 solutions. Okay, so next time I'll just do some more examples. Lots of different things can happen. Okay, see you next time.